Hello, everyone. In this video, we will discuss the extreme values of a function. Extreme values, also known as extrema. First, let us introduce absolute extrema, or global extrema. These are the maximum and minimum values of a function on its domain. As an example, please consider the graph of a function defined on a closed interval. The absolute maximum is the highest value of the function within its domain, or it is the highest point on the entire curve. Meanwhile, the absolute minimum is the lowest value of the function within its domain, or it is the lowest point on the entire curve. Next, let us discuss relative extrema, or local extrema. These are the maximum and minimum values of a function on an open interval, or a portion of the domain of the function. A relative maximum is the highest value of the function on an open interval, or it is the highest point in a portion of the curve. Meanwhile, a relative minimum is the lowest value of the function on an open interval, or it is the lowest point in a portion of the curve. The left endpoint is neither a relative nor an absolute maximum, and the right endpoint is not a relative maximum because they are both at the endpoints of the domain, and they cannot be contained inside an open interval. Not every open interval in the domain contains a relative extremum. Suppose we choose this open interval. Because an open interval does not include its endpoints, then this open interval does not have relative extrema. Now, suppose the function is defined on an open interval. Because both endpoints are not included in the domain, then they are excluded from being considered as absolute or relative extrema. The left endpoint is not a relative nor an absolute maximum, and the right endpoint is not a relative nor an absolute maximum. In conclusion, the graph has an absolute minimum but no absolute maximum. Now, consider a function defined on the open interval, the real line. Because both endpoints are not included in the domain, then they are excluded from being considered as absolute or relative extrema. In conclusion, the graph has an absolute minimum but no absolute maximum. The extreme value theorem. This theorem guarantees the existence of both absolute maximum and absolute minimum values for a function that is continuous on a closed interval. Please consider the following graph of a continuous function on a finite closed interval. Because the function is continuous, the extreme value theorem guarantees that the function has both an absolute maximum and an absolute minimum somewhere in the closed interval. Moreover, the extreme value theorem implies that if a function is discontinuous on a closed interval, or continuous on an open interval, the function may have only one extreme value or none at all. While the extreme value theorem affirms the existence of both absolute extrema, it does not provide a method on how to find these values. In the following discussion, we will establish concepts on how to find these extreme values. Critical numbers. A critical number is a number in the domain of a function such that the derivative of the function at that number is equal to 0. Recall that the derivative of a function at a number refers to the slope of the tangent line to the function at that number. Also, a straight line with a zero slope is a horizontal line. A critical point that satisfies this condition is called a stationary point. Consider the following graph of a function. A critical number leads to a point where the tangent line is horizontal. A theorem about critical numbers is given by Fermat's theorem. It says that if a function has a relative extremum at a number and the derivative at that number exists, it must be that the derivative is equal to 0. Simply stated, if a function has a relative extremum at a number, then that number is a critical number of the function. A critical number is also a number in the domain of a function such that the derivative of the function at that number does not exist. A critical point that satisfies this condition is not a stationary point. Recall the definition of the derivative of a function at a number. Consider the following graphs of two different functions with a sharp turn and a cusp. A critical number may lead to a point where the one-sided derivatives are not equal. Hence the derivative at the number does not exist. In other words, each of these functions is not differentiable at the critical point. This can be verified by getting the derivative of the function, and see that the denominator cannot be 0. In both examples, there is a relative extremum at the critical number. Next, consider the graph of a function with a vertical tangent line. Recall that the slope of a vertical line is undefined. A critical number may also lead to a point where the derivative at that number is infinite. Hence the derivative at the number does not exist. Now, consider the graph of a function with an infinite discontinuity. A critical number is where the function has an infinite discontinuity. Hence the derivative at the number does not exist. Each of these functions is not differentiable at the critical point. The closed interval method. To be able to find the absolute extrema of a function on a closed interval. First, determine the critical numbers in the corresponding open interval. Do this by differentiating the function, equating it to 0, and solving for the roots of the equation. Second, compute the value of the function at the critical numbers. Third, compute the value of the function at the endpoints. Fourth, the absolute maximum is the highest among the computed values, while the absolute minimum is the lowest among the computed values. Please refer to the following graph of a continuous function on a closed interval. A critical number in the open interval has a tangent line of slope equal to 0. The function provides value at each critical number and endpoint. The highest point refers to the absolute maximum, while the lowest point refers to the absolute minimum. Example: find the absolute extrema of the following function. On the closed interval -2, 1.5. Solution. Let us first confirm that the given function is continuous on the given closed interval. Because the function is a polynomial function, then it is continuous everywhere, and in this case, it is continuous on the given closed interval. Then determine the critical numbers of the given function at the corresponding open interval. A critical number is where the derivative of a function becomes 0. So, differentiate the given function and equate it to 0. Then find the roots of the equation, or the values that make the left side of the equation equal to 0. The equation has the following roots. Two critical numbers are inside the open interval. while the other one is one of the endpoints of the closed interval. Next, find the value of the function at the critical numbers. Substitute each critical number into the given function. And then find the value of the function at the endpoints of the open interval. Substitute each endpoint into the given function. Finally, determine the absolute extrema. The absolute maximum is the highest value, while the absolute minimum is the lowest value. The following figure shows the graph of the given function on the given closed interval. The absolute maximum is attained at the highest point on the curve, while the absolute minimum is achieved at the lowest point on the curve. Even without a graph, we are confident that these are the absolute extrema of the given function on the closed interval because: first, we have confirmed earlier that the function is continuous on the closed interval. And second, the absolute extrema were computed from the critical numbers, although in other cases, absolute extrema can occur at the endpoints, just like in the previous pages. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.